Matthew Syed, author of Rebel Ideas, The Power of Diverse Thinking, argues that individual intelligence is no longer enough, that the only way to tackle complex problems is to harness the power of cognitive diversity. This is very true when it comes to solving socio-environmental problems. It is all about teams of people who see the world differently, but are willing to engage in social learning to embrace uncertainty and seek more sustainable environmental and social futures. Welcome to Succinct's Learning Series on Socio-Environmental Modeling. I'm Margaret Palmer, Director of Succinct and also Professor at the University of Maryland. This is part 2 of the 3-part tutorial on building the basics for socio-environmental modeling. It focuses on why defining the problem and even the nature of the socio-environmental system is non-trivial. It also delves into processes for accomplishing that, which involves modeling teams that must get together to span boundaries between the beliefs and disciplinary differences between team members. In part 1 of this tutorial, we discuss socio-environmental systems as complex adaptive systems that are highly dynamic. These types of systems have also been the subject of extensive modeling, including, for example, the production of economic forecasts, or exploring even the future impacts of new road networks. However, as we will explain shortly, to understand and model socio-environmental systems, we have to go beyond their attributes as complex adaptive systems, and we have to explore how they can be modeled. Okay, recall in this simple diagram we've talked before about the 4 basic modeling phases. The first step is defining the socio-environmental problem and what motivated the modeling effort. In the second phase, we have to conceptualize the problem in a system context that includes components and processes linking them. Third, the more technical aspects of the model formalization process begins. And then the final step in the process is, of course, the application of the model. I want you to note there's an arrow from this phase back to step 1 because often the outcomes from the model motivate new questions or a need to make changes to the model. In this video, we're focusing on processes, especially team processes, that are part of the first and second modeling phases. And one thing influencing those processes is that socio-environmental problems, that is, what motivates many modeling efforts, are vexing because they fall into a class called wicked problems. Now, there are many definitions of what a wicked problem is, but they almost always include the following. They're characterized by, first, limitations on how you can study them. Second, differences in opinion on possible solutions. They also are characterized as almost always being linked to bigger underlying problems. And fourth, they're unique in place or time. So let's delve just a little more into each of these. For obvious reasons, controlled experiments or testing hypothesized solutions can't be done. So that's what I meant when I said there are limitations on how you can study them. For a socio-environmental problem, we don't have the freedom to say, well, what if we assume the solution is to only allow every person to consume X amount of water every day? Obviously, we can't do experiments like that with people. Now, when it comes to problems at the interface of people and the environment, it's also true that there are no right answers. Rather, there are what I call distributions of solutions. The way the problem or system is conceptualized or described influences that solution set. And that conceptualization can also be influenced by many factors such as individual values, local policies, the status of natural resources, etc. The result is that any one solution that may seem ideal to some may have impacts on others. Wicked problems are also usually characterized by being linked to other underlying problems. In the case of water, perhaps scarcity in a region leads to conflicts associated with water use. Say in one region, farmers pump excessive amounts of groundwater for irrigation, but this results in nearby regions having a hard time meeting basic water needs. So fights over water rights ensue. Now, at one level, the basic problem is that farmers are using too much water. But perhaps underlying that is the fact that the region is getting less rainfall due to a changing climate. And what is underlying climate change is excessive use of fossil fuels regionally and globally. So understanding the problem is like peeling the layers of an onion. There's always more and more beneath each layer. Wicked problems are also characterized by being unique in the sense that they are context dependent. So a solution to a water dispute in one place may not work in another. Much like ecosystem services, socio-environmental systems are place-based, and so are their problems. Fortunately, by studying cases, we can accrue knowledge about the fundamental social and environmental processes that can help us when related cases begin to arise. So, what are the modeling implications that stem from socio-environmental problems being wicked problems? Well, one is that they have higher levels of uncertainty than so-called normal problems. Now, much of this is associated with the need to engage in interdisciplinary and transdisciplinary teamwork and the need to develop model frameworks that vary by the specific context of the case. So while all modeling comes with uncertainty, and this can be high for complex adaptive systems, socio-environmental modeling accrues uncertainty at every step in the modeling process, not just, for example, in the parameters. This is well described by Sandis El-Sawa and colleagues in their article on the 8 grand challenges of socio-environmental modeling. They call this multi-sourced uncertainty, deep uncertainty.
In the modeling literature, the main sources of uncertainty are often attributed to data, model structure, and model parameters. But we know that this is a very partial view of uncertainty. Uncertainty sources extend beyond the model-only sources and pertain to every modeling choice, activity, and product, intermediate and final, generated throughout the modeling process.
Digging into what Sandis said, let's just talk about that a bit. Since people vary in how they view socio-environmental problems, or even if there's a problem at all, one source of uncertainty can be associated with the team processes used to develop the model. People developing it may have different views or motivations on what is important to include in the model. For example, there's no one way to depict the system and problems associated with that, and such differences can go beyond just personal values and views because socio-environmental modeling requires teams of people with diverse expertise. Interdisciplinary collaborations that include scholars from different fields are the norm, and as we'll discuss in a minute, stakeholders are often part of modeling teams. In terms of disciplinary expertise required, I'm not talking about like a chemist and a biologist working together. Instead, collaborators are far more interdisciplinary. So a team, for example, could include a hydrologist, an ecologist, an anthropologist, and a soil scientist, maybe even a computer scientist. These are researchers from scholarly cultures that are very different, not just in terms of language, but in their methods and their fundamental epistemologies. Agreeing on what is in and what is out of the model varies with who's in the room and is part of a negotiation process by the team. That negotiation requires a lot of work to understand different disciplinary perspectives, norms, and practices. In 2008, Thaddeus Miller and colleagues published a paper on the nature of such differences. In generalizing, they described 3 very different scholarly traditions that teams may need to navigate in their modeling process. I'll briefly mention these just to illustrate that how knowledge is acquired and validated can be quite different between team members from different disciplines. Some may take a mechanistic or positivist approach, relying heavily on the scientific method, while others may view knowledge as contingent, varying with context, while still others may approach knowledge as constructivist. Now, as alluded to, socio-environmental modeling is not just about teams of scholars. Many modeling teams also include stakeholders and what Succinct likes to call potential users of the project findings. These are those who care about the problem or who may win or lose based on the solution space. Such teams, sometimes described as transdisciplinary, help define the problem, structure the research, and they should collaborate throughout. What is useful about their inclusion is that they keep scholars focused on real-world problems, and in particular, solution spaces that are not unachievable. Some policies simply aren't possible.
Just remember to.
So the inclusion of stakeholders means that socio-environmental collaborations can be intersector as well as interdisciplinary. And when this is the case, it is often not only individual views and values that can differ, but the very goals of the research. Stakeholders often seek specific information or tools that make their jobs easier. Researchers may be more interested in the production of new knowledge or teaching resources, or simply, a lot of us just want a few publications. Given the potential team diversity and different ways of thinking, what information is needed or is even legitimate in the eyes of some team members can be highly contested. For example, say a team is focused on food security. Different views on what this means and what is relevant in model development will likely vary. Is it about primary productivity, water availability, or soil health? Or is it about access to trade, perhaps gender differences, or trade policies, or both? But diverse views is not bad. They simply need to be recognized and discussed so the group can reach consensus. Discussions, especially those involving conflict resolution, lead to what's called social learning by the team. The processes of reconciling different views, overcoming differences in language, understanding visual cues of team members, and creating shared experiences actually shift the social environment in a more open and creative direction. And there's substantial research to support this, that these projects tend to be more creative and highly cited. As a group, teams learn to negotiate the differences that range from divergent views and understandings, distinct epistemologies, and even differences in goals or the way the problem needs to be approached. To accomplish this negotiation, cognitive psychologist Stephen Fior talks about the importance of team metacognition. That means not just being aware of your own thinking about the problem, but paying close attention to what is going on in the discussion. How others are thinking, for example, how they look, their body language.
So you're thinking about what is the problem you're trying to solve. So you're reflecting on your own cognitive processes and trying to understand the situation, and you're also trying to understand the team dynamic that's going on within that team. So this kind of metacognitive activity in science teams could be, for example, well, is the environmental scientist really understanding what the economist is saying about this particular problem? Or do they just disagree because they have a different fundamental worldview? So you would need to be metacognitive from the standpoint of, is a disagreement that's emerging due to a lack of understanding? Or is a disagreement that is emerging due to the fact that they just don't think that this is the appropriate way to solve that problem? Because as you're well aware, economists see the world in a certain way, environmental scientists see the world in a certain way, psychologists see the world in a certain way, and you need to be metacognitive about these worldviews in order to come to an integrated understanding of the kind of scientific collaboration that you're trying to pursue.
A growing body of research by people like Fior has focused on dynamics that relate to learning processes at the team level. In fact, one of Succinct's core objectives has been to provide resources to accelerate team progress and help them deal with some of the hurdles they are likely to face. We have a number of online resources on that you can tap. These help with combating diverse forms of data. I called this knowledge earlier, overcoming computational problems, and they include tips on things like how to assemble teams and prepare them for novel work, how to facilitate meetings, either by the leader of the group, someone in the group, or an outside expert, and processes you can use in navigating the co-development and conceptualization stages work. In fact, let's take a detour and focus for just a minute in the conceptualization process. Recall, it's one of the first steps in modeling. It is critical that the team has thought about the process they will use to reach agreement on how the socio-environmental system being studied is structured, its components, what interacts with what, and over what temporal and spatial scales. We found at Succinct it's not a good idea to split in disciplinary teams to do this, even though it's tempting and seems easier. As an alternative, leaders could ask every individual to think carefully and alone about his or her own understanding of the problem, jotting down notes to share along with a visual depiction of their understanding. Then coming back together as a team, they discuss the different understandings and try to arrive at a shared mental model of the problem and what knowledge, in what form, they need to address the problem. The shared depiction or mental model is often developed by working together to integrate the individual perspectives. Each member's visual depiction, along with their explanation, has been brought back to the team. And there are tools to help with this. There are also existing frameworks or general ways to conceptualize socio-environmental systems and problems, and the team can build on these. Let me give you a few examples of depictions and frameworks teams have developed. It's important to note that these are not mere cartoons. Rather, the team understands what is embedded in these models or in these depictions, which includes, for example, the components they consider important, how they're connected, and what knowledge the team will draw upon. So as an example, Terry Chapin and colleagues focused on the sustainability of Alaskan forests under climate change. They developed a framework to illustrate that there are processes and forces exogenous to the socio-ecological system those forces influence. These include regional governance and climate in their case. But it is not just cross-scale interactions spatially that you'd have to include in the model, but temporal interactions that span scales. So in Terry's example framework, some variables like soil resources and property, as well as use rights, change slowly, while nutrient concentrations and community income change quickly. In the socio-environmental literature, these are often referred to as slow and fast variables or components. Now, another framework is called the DIPSR framework. It has been used for environmental assessment to aid in policy decisions and most generally for environmental management. The 5 categories it includes are where the DIPSR acronym comes from: driving forces, pressures, state of the environment, the impacts, and the responses. The framework suggests a model design that links cause and effect relationships among these 5 categories, and it's one of the oldest tools for depicting socio-environmental systems, having been used since the early 1980s. And interestingly, it's still used today, mostly in environmental statistics and risk assessment. And then a framework that I can't leave out, even in this very short tutorial, is one that comes from the work of Nobel Prize-winning economist Elinor Ostrom. She focused extensively on governance of common pool natural resources. The action arena is where individuals acting on their own or as agents of formal organizations interact with each other and thus jointly affect outcomes that are differentially valued by the actors. This diagram is actually a simplified version that came out with her article in Science in 2009. It's used today in more detailed forms, and in those, the arena can be broken down into many types of interactions. For example, in a slightly more detailed form of the framework that was developed by Michael McGinnis and Professor Ostrom, the components are considered multi-tiered, as illustrated by the 4 stacks of files. The resource and governance conditions, the top left and right blocks, influence the interactions which involve the governance system and the actors. The feedbacks are indicated with a dashed line. And note, this SE system is embedded in a broader social, economic, and political setting. This framework from the Ostrom workshop was meant to help standardize language and facilitate the testing of different theories, processes, and outcomes that are critical in different settings. It has proven to be relevant for use in explaining sustainable outcomes in the management of forestry, fishery, and water resources. Now, there are many other frameworks in the literature. The ones I've shown here can be used as the basis for extending them to mathematical or other types of formal models in which the functional relationships among components are described. Exactly how that is done, that is, how the model is formalized, depends a lot on the goals of the modeling team. In other words, what is the purpose of the model, including what type of output is needed? And we address this in part 3 of this Building the Basics tutorial. As an entree to that, I now recap what we've covered in part 2. We largely focused on the first 2 steps of the modeling process. We talked about building inter- or transdisciplinary teams that help define the problem and the need to decide as a group on the objectives of the model. For some teams, this may be strongly influenced by stakeholders. We also talked about the many difficulties teams can face in agreeing not only on the problem definition, but on the structure of the socio-environmental system, its components, and interactions. We ended with talking about the frameworks that need to be developed to help with the next step, which is actually formalizing the model. So I want to close today by thanking the core group of scholars who helped conceptualize the tutorial, the Succinct series on socio-environmental modeling. As said at the end of the Part 1 video, they are from multiple countries with multiple backgrounds and experiences, but all are very enthusiastic about modeling socio-environmental systems. Thank you for listening, and I encourage you to go on to Part 3.